Hello and welcome. In this video, we will explore the fundamental concepts of differential calculus, a cornerstone of the IB mathematics analysis and approaches higher level curriculum. By the end of this session, you will be able to, first, understand the concept of a gradient function and how it relates to the gradient of a tangent line. Second, define the derivative of a function using the limit definition, also known as differentiation from first principles. And third, apply this definition to find the derivatives of various functions, including polynomials and trigonometric functions. These skills are essential for understanding rates of change and optimization problems, which are central to higher-level mathematics. Let's begin by exploring the idea of a gradient function. Imagine a curve, y equals f of x. At any point on this curve, we can draw a straight line that just touches the curve at that single point. This line is called the tangent. The gradient, or slope, of this tangent line tells us the instantaneous rate of change of the function at that specific point. It tells us how steep the curve is at that exact location. Now, if we move to a different point on the curve, the steepness will likely change, and so the gradient of the tangent line will also change. This observation leads to a powerful idea. For many functions, the gradient of the tangent is not a constant number, but rather a value that depends on the x-coordinate. This relationship can be described by a new function. This new function, which gives us the gradient of the tangent at any point x, is called the gradient function, or the derivative, and is denoted as f prime of x. So, the gradient function f prime of x is a function that, for any given x value, outputs the gradient of the tangent to the original function f of x at that x value. Let's investigate this concept with some simple functions. First, consider a constant function. For example, let f of x equal 4. This is a horizontal line. What is the gradient of this line? It's 0. And this is true for any point on the line. The steepness never changes. Therefore, the gradient function for f of x equals 4 is f prime of x equals 0. The derivative of a constant is always 0. Next, let's look at a linear function. Consider f of x equals 3x plus 2. This is a straight line with a gradient of 3. Just like the constant function, the gradient of a straight line is constant. It's the same at every point. So, the gradient function for f of x equals 3x plus 2 is f prime of x equals 3. The derivative of a linear function is its gradient. These examples show that for straight lines, the gradient function is simply the constant gradient of the line itself. The steepness is uniform. Now, let's consider a function where the gradient is not constant. A classic example is a quadratic function. Let's take f of x equals x squared. This is a parabola. If we draw a tangent at a point like x equals minus 2, the line is steep and goes downwards. The gradient is negative. At the vertex, x equals 0, the tangent is a horizontal line. Its gradient is 0. And at a point like x equals 2, the tangent is steep and goes upwards. The gradient is positive. The gradient is clearly changing. It's negative, then 0, then positive. This means the gradient function, f prime of x, cannot be a constant. In fact, for f of x equals x squared, the gradient function is f prime of x equals 2x. This is a linear function. Let's check this. At x equals minus 2, f prime of minus 2 is 2 times minus 2, which is minus 4, a negative gradient. At x equals 0, f prime of 0 is 2 times 0, which is 0, a 0 gradient. And at x equals 2, f prime of 2 is 2 times 2, which is 4, a positive gradient. This matches our observations. This example demonstrates that the gradient function can be a different type of function than the original. Here, a quadratic function has a linear gradient function. So how do we find these gradient functions rigorously? We use a method called differentiation from first principles. This method is based on the idea of a limit. Let's consider a curve y equals f of x. We want to find the gradient of the tangent at a general point A with coordinates x, f of x. We can't find the gradient of a single point, but we can find the gradient of a line connecting 2 points. So let's pick another point, B, very close to A. Let the x-coordinate of B be x plus h, where h is a small number. The y-coordinate will then be f of x plus h. Now we can calculate the gradient of the chord. the straight line segment connecting A and B. The gradient of the chord AB is the change in y divided by the change in x. This is f of x plus h minus f of x, all divided by h. This chord is an approximation of the tangent line. To make it a better approximation, we need to make point B closer to point A. We do this by making the distance h smaller and smaller. As h approaches 0, the chord AB becomes the tangent line at point A. The gradient of the chord approaches the gradient of the tangent. This leads us to the formal definition of the derivative. The derivative of f of x, denoted f prime of x, is the limit as h approaches 0 of the expression f of x plus h minus f of x, all divided by h. This is the definition of the derivative from first principles. It is the foundation of all differential calculus. Let's apply this definition to find the derivative of a polynomial function. We'll work through an example step by step. Consider the function f of x equals x cubed. Our goal is to find its derivative, f prime of x, using first principles. First, we write down the definition of the derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Next, we substitute our function into this formula. We need to find f of x plus h. Since f of x is x cubed, f of x plus h is simply x plus h cubed. Now we substitute this back into the limit expression. F prime of x equals the limit as h approaches 0 of the quantity x plus h cubed minus x cubed all over h. The next step is to expand the term x plus h cubed. We can use the binomial theorem or simply multiply it out. X plus h cubed expands to x cubed plus 3x squared, h plus 3x, h squared plus h cubed. Now substitute this expansion back into our limit. F prime of x equals the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Notice that the x cubed terms cancel out. This leaves us with the limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed all over h. Now we can factor out an h from the numerator. This gives us the limit as h approaches 0 of h times the quantity 3x squared plus 3xh plus h squared all over h. Since h is approaching 0 but is not equal to 0, we can cancel the h in the numerator and denominator. We are left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Finally, we can evaluate this limit by substituting h equals 0. This gives us 3x squared plus 3x times 0 plus 0 squared, which simplifies to 3x squared. So, we have found that the derivative of f of x equals x cubed is f prime of x equals 3x squared. This means that for any x value, the gradient of the tangent to the curve y equals x cubed is given by 3x squared. Let's try another polynomial example, this time with a quadratic function. We will find the derivative of f of x equals x squared minus 3x from first principles. Again, we start with the definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. First, let's find f of x plus h. We replace every x in the function with x plus h. So, f of x plus h is the quantity x plus h squared minus 3 times the quantity x plus h. Now, we expand this expression. X plus h squared is x squared plus 2x h plus h squared. And negative 3 times x plus h is negative 3x minus 3h. Now we substitute this and f of x back into the limit formula. F prime of x equals the limit as h approaches 0 of the entire expression for f of x plus h minus the original function f of x all over h. Let's simplify the numerator by distributing the negative sign and combining like terms. The x squared terms cancel and the negative 3x terms cancel. We are left with 2xh plus h squared minus 3h. As before, we can factor out an h from the numerator. This gives us the limit as h approaches 0 of h times the quantity 2x plus h minus 3, all over h. We can cancel the h terms. We are left with the limit as h approaches 0 of 2x plus h minus 3. Finally, we evaluate the limit by setting h to 0. This gives us 2x plus 0 minus 3, which is 2x minus 3. So the derivative of f of x equals x squared minus 3x is f prime of x equals 2x minus 3. This means the gradient of the tangent to the parabola changes linearly with x. In addition to the f prime of x notation, there is another common way to represent the derivative, especially when a function is given in the form y equals f of x. This is called Leibniz notation, and it is written as dy over dx. It is read as dy by dx, or the derivative of y with respect to x. This notation emphasizes the idea of a rate of change. The d in dy and dx can be thought of as representing an infinitesimally small change. So dy over dx is the ratio of an infinitesimally small change in y to an infinitesimally small change in x. It's crucial to remember that dy over dx is not a fraction in the traditional sense. It's a single symbol representing the derivative. However, the notation is very suggestive of the limit definition we just learned. If we replace h with delta x, and f of x plus h minus f of x with delta y, the limit definition becomes the limit as delta x approaches 0 of delta y over delta x, which is exactly what dy over dx represents. Both f prime of x and dy over dx mean the same thing, the derivative of the function. You should be comfortable using either notation. Let's use Leibniz notation in an example. We'll find the derivative of a cubic function. Given y equals x cubed minus 2x squared plus 3, we want to find dy over dx from first principles. We'll use the same limit definition, just with y and x. dy over dx equals the limit as h approaches 0 of f of x plus h minus f of x all over h. First, let's find f of x plus h. F of x plus h is the quantity x plus h cubed minus 2 times the quantity x plus h squared plus 3. Now we expand this expression. X plus h cubed is x cubed plus 3x squared, h plus 3x h squared plus h cubed. And negative 2 times x plus h squared is negative 2 times the quantity x squared plus 2xh plus h squared, which simplifies to negative 2x squared minus 4xh minus 2h squared. Now, we substitute this and f of x into the limit formula. dy over dx equals the limit, as h approaches 0 of the entire expression for f of x plus h, minus the original function f of x, all over h. Let's simplify the numerator. The x cubed, negative 2x squared, and 3 terms all cancel out. We are left with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed minus 4xh minus 2h squared, all over h. Factor out an h from the numerator. This gives us the limit as h approaches 0 of h times the quantity 3x squared plus 3xh plus h squared minus 4x minus 2h, all over h. Cancel the h terms. We are left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 4x minus 2h. Finally, evaluate the limit by setting h to 0. This gives us 3x squared minus 4x. So the derivative of y equals x cubed minus 2x squared plus 3 is dy over dx equals 3x squared minus 4x. Now, let's tackle a more challenging example, finding the derivative of a trigonometric function. This requires using some special trigonometric limits. We will prove that the derivative of f of x equals sine x is f prime of x equals cosine x. We start with the first principles definition. F prime of x equals the limit as h approaches 0 of sine of x plus h minus sine x all over h. Here, we need to use the trigonometric identity for the sine of a sum of angles. Recall that sine of a plus b equals sine a cosine b plus cosine a sine b. Applying this to our expression, with a equals x and b equals h, f prime of x equals the limit as h approaches 0 of sine x cosine h plus cosine x sine h minus sine x all over h. Now, we can rearrange the terms in the numerator to group the sine x terms. This gives us the limit as h approaches 0 of sine x times the quantity cosine h minus 1 plus cosine x sine h all over h. We can split this into two separate fractions. F prime of x equals the limit as h approaches 0 of sine x times the quantity cosine h minus 1 over h plus cosine x times the quantity sine h over h. Since x is independent of h, we can pull sine x and cosine x out of the limit. This gives us sine x times the limit of cosine h minus 1 over h plus cosine x times the limit of sine h over h. Now we need to evaluate these two special trigonometric limits. These are standard results you should be familiar with. The limit as h approaches 0 of sine h over h is 1, and the limit as h approaches 0 of cosine h minus 1 over h is 0. Substituting these values back into our expression, f prime of x equals sine x times 0 plus cosine x times 1. This simplifies to cosine x, and we have successfully proven that the derivative of sine x is cosine x. Let's recap what we've learned. We started with the idea of a gradient function, f prime of x, which gives the gradient of the tangent to a curve y equals f of x at any point. We then established the formal definition of the derivative from first principles, which is based on the limit of the gradient of a chord. We saw how to apply this definition to find the derivatives of polynomial functions and even a trigonometric function like sine x. This process of finding the derivative is called differentiation. You are now able to understand the concept of a gradient function, define the derivative using first principles, and apply this definition to find derivatives. These are essential skills for your IB, AAHL studies. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Question 1. Find the derivative of f of x equals 2x squared minus 5x plus 1 from first principles. Question 2. Given y equals x cubed plus 4x, find dy over dx from first principles. Question 3. Find the gradient of the tangent to the curve f of x equals 1 over x at the point where x equals 2. Question 4. Prove that the derivative of f of x equals cosine x is f prime of x equals negative sine x. Question 5. Find the points on the graph of y equals x cubed minus 3x where the tangent has a gradient of 0. Let's go through the solutions. Here is the solution for question 1. We start with the definition. F of x plus h is 2 times x plus h squared minus 5 times x plus h plus 1. Expanding this gives 2x squared plus 4xh plus 2h squared minus 5x minus 5h plus 1. Substituting into the limit formula, the 2x squared, negative 5x, and 1 terms cancel, we are left with 4xh plus 2h squared minus 5h. Factoring out h and canceling, we get the limit of 4x plus 2h minus 5. Evaluating the limit gives 4x minus 5. So, the derivative is 4x minus 5. Here is the solution for question 2. We use the Leibniz notation. F of x plus h is x plus h cubed plus 4 times x plus h. Expanding this gives x cubed plus 3 x squared h plus 3x h squared plus h cubed plus 4x plus 4h. Substituting into the limit formula, the x cubed and 4x terms cancel. We are left with 3x squared h plus 3x h squared plus h cubed plus 4h. Factoring out h and canceling, we get the limit of 3x squared plus 3xh plus h squared plus 4. Evaluating the limit gives 3x squared plus 4. So the derivative is 3x squared plus 4. Here's the solution for question 3. We need to find the derivative of f of x equals 1 over x. F of x plus h is 1 over x plus h. Substituting into the limit formula, we get the limit of 1 over x plus h minus 1 over x, all over h. We combine the fractions in the numerator. This simplifies to the limit of negative h over x times x plus h, all over h. Canceling the h terms, we get the limit of negative 1 over x times x plus h. Evaluating the limit gives negative 1 over x squared. The question asks for the gradient at x equals 2, so we substitute 2 into our derivative. F prime of 2 equals negative 1 over 2 squared, which is negative 1 over 4. The gradient of the tangent at x equals 2 is negative 1/4. Here is the solution for question 4. We need to prove that the derivative of cosine x is negative sine x. We start with the definition. We use the trigonometric identity for the cosine of a sum of angles. Recall that cosine of a plus b equals cosine a cosine b minus sine a sine b. Substituting this into our limit, we get the limit of cosine x cosine h minus sine x sine h minus cosine x, all over h. Rearranging and splitting the fraction, we get cosine x times the limit of cosine h minus 1 over h minus sine x times the limit of sine h over h. Using our special limits, this becomes cosine x times 0 minus sine x times 1, which simplifies to negative sine x. The proof is complete. Finally, here is the solution for question 5. We need to find the points where the tangent to y equals x cubed minus 3x has a gradient of 0. First, we need to find the derivative. Using the same method as in question 2, we find that the derivative, dy over dx, is 3x squared minus 3. The question states that the gradient is 0, so we set our derivative equal to 0. 3x squared minus 3 equals 0. We can solve this equation for x. Adding 3 to both sides gives 3, x squared equals 3. Dividing by 3 gives x squared equals 1. Taking the square root of both sides, we find x equals positive or negative 1. These are the x-coordinates of the points. To find the full coordinates, we substitute these x values back into the original function, y equals x cubed minus 3x. For x equals 1, y equals 1 cubed minus 3 times 1, which is negative 2. This gives the point 1 minus 2. For x equals negative 1, y equals negative 1 cubed minus 3 times negative 1, which is 2. This gives the point minus 1, 2. So the 2 points on the graph where the tangent has a gradient of 0 are 1, minus 2, and minus 1, 2. These points correspond to the local maximum and local minimum of the function. That concludes our exploration of differentiation from first principles. You have now seen the rigorous foundation of calculus. While this method is essential for understanding the definition, in practice, we will learn more efficient rules for differentiation. However, the first principles definition is the source of all those rules. Thank you for watching. Keep practicing these concepts to build a strong foundation for your IB mathematics journey.